Linear regression attempts to find the relationship between a set of input features and a target value. Let's say we have two sets of features, height and age, and a third target value, weight. Linear regression attempts to predict any person's weight given their height and age by finding the line of best fit on given data through this equation. You can think of these coefficients we're multiplying height and age by as a measure of their relative importance. Since I think height is proportional to weight, while age is proportional to weight only up to a certain value, I'm going to times height by a greater value. And since this equation is just an application of this equation, I'm going to add an intercept. Logistic regression attempts to find the probability that an object belongs to a class, given a set of input features. It is similar to linear regression in that we have input features, each assigned relative importance through a larger or smaller coefficient, and a negative coefficient if the correlation between a given feature and the target value is negative. But unlike linear regression, logistic regression outputs a value between 0 and 1. An output of 1 represents that the algorithm is certain that the object belongs to a class, while an output of 0 represents certainty that the object does not belong to the class. To convert a target value that with the linear regression algorithm could resolve to any value between negative infinity and infinity, you generally use the sigmoid function. When you have multiple classes, for example, normal weight, underweight, and overweight, you compute the probabilities for each class, then use the class that the algorithm is most confident the object belongs to. Support vector machines try to divide our dataset into classes with an imaginary plane that is optimized to reduce the number of misclassifications and maximize the distance between classes. Naive Bayes classifiers use the Bayes theorem to break down the problem of deciding which category an object belongs to. The probability that an object belongs to a class is equivalent to the probability that the class has a set of features the object has, multiplied by the probability that any object is of that class, divided by the probability that any object has that specific set of features. When we have multiple features as we normally do, we can break down the problem further through the mathematical formula that the probability of an object having feature A and feature B is equivalent to the probability that an object has feature A times by the probability that an object has feature B. Now, I'll leave the exact computation of this down to an exercise for the reader. Here, O represents octogenarian. So anyone who's over 80. K nearest neighbors predicts the target value of an object by taking K, an arbitrary value you decide, nearest data points, and averaging their target values. How do we measure what is near? We calculate the Euclidean distance using the formula squaring the distance between each input feature. For example, we're predicting the weight of a person given their height and age with K equals 3. We'd find the 3 nearest data points in terms of the square roots of the sums of differences in age and height. We'd get the weights of these 3 nearest points and average them to predict the weight of a person given their height and age. The decision tree works by finding a boundary that best divides our data points into classes. We repeat this process of finding a boundary for each feature. It's similar to the SVM algorithm, except SVM is more complex as it captures the relative importance of each feature, whereas the decision tree assumes all features are independent of one another. The random forest is a variation of the decision tree algorithm. Instead of a single decision tree, the random forest averages the results of multiple decision trees. You might ask, but isn't that the same thing as having a single, more complex decision tree? Not quite. Each decision tree within a random forest includes a subset of features randomly samples. This reduces the possibility that a single feature is far overvalued by the algorithm while other features are ignored. Random forests take longer to train and produce more accurate results.